Hello and welcome to my talk today. My name is Matthew Fisher and I will be talking about adaptive algorithms in Bayesian quadrature. So first of all, this talk is based on a paper co-authored between me, Matthew Fisher, Chris Oates, Catherine Powell and Aretha Tekentrup called a locally adaptive Bayesian cubature method. So this is in the proceedings of AI Stats 2020. So if you are interested in the materials in this talk today, you can find more details in the paper here. Right, so the contents of this talk are the following. So in order to actually discuss adaptive algorithms in Bayesian quadrature, we need to know what Bayesian cubature is. So first, a thing to note is that cubature and quadrature are synonymous, so I'm going to use them interchangeably. So we need to know what Bayesian cubature is. Second of all, we need to know what adaptivity means. And finally, we can actually start discussing what adaptive algorithms in Bayesian cubature. Okay, so first of all, what's Bayesian cubature? In order to discuss what Bayesian cubature is, we need to discuss what cubature is. And so all cubature is the numerical approximation of an integral, I of f star, where f star is our integrand over a domain D that we assume to have no closed form integral, and therefore we have to numerically estimate it using what's called a cubature rule. So the classical approach to cubature has the following components. The first is the problem at hand, the integral problem. The second is cubature rule, which is a weighted sum of integrand evaluations. And finally, we have the error, the true error, which is the difference between the integral and its approximation, the cubature rule. So as an example, suppose our integrand is this blue squiggly line, f star, and we evaluate it at a predetermined set of points, these red dots here, and we want to perform a cubature rule. So cubature rules are typically, though not always, driven by an interpolatory scheme. So for example, if we have a linear interpolatory scheme, we get something called the trapezium rule, which I'm sure you're familiar with. And as you can hopefully see, is that this is actually our cubature rule. It's a weighted sum of integrand evaluations. Okay, so errors in classical cubature. So I wrote before about the true error, which is the absolute difference between the true integral and its numerical approximation, the cubature rule. However, we can't actually compute it. We can, however, estimate it, and there are a number of ways of doing this. One, which is pertinent to this talk, is called local error estimates. And so a local error estimate is the difference between two cubature rules, the absolute difference between two cubature rules. And so the intuition is that if you imagine Q1 is a cubature rule, but the point set chosen is on a much finer mesh than Q2, then this Q1 is a much closer approximation to the true value of the integral, and therefore the absolute difference between Q2 and Q1 is an approximation of the true error epsilon. And so errors of this form are called local error estimates. So another approach. Okay, so as before, a cubature rule, in a cubature problem, or numerical integration problem, you only ever have finite discrete information about your function, f star, your integrand, f star. And so we actually know what the function's doing at these red dots, and in between these red dots, we actually have no idea what's going on. Well, we might have some intuition, but the thing to recognize is that there's inherent uncertainty in the problem. And so really what we would like to do is quantify the uncertainty in some way. And so one way of doing it is through a stochastic process method. So essentially you have a random function that you constrain to go through the red points, and then you can integrate the random function and you can push forward the uncertainty inherent in the random function constrained to the points onto its integral, the integral of the random function. So as an example, let's pick a stochastic process that looks like this. So there's many to choose from, an infinite number. So this example is called Brownian motion. And so on the left, we have a sample from the stochastic process. And on the right, we have the integral of its sample. And so what we can see is if we repeatedly sample and integrate each one of the samples, we form an empirical measure of the integral of the stochastic process. And so here, if we collect all our samples together, we can see that the integral of the stochastic process constrained into these dots is Gaussian, or looks Gaussian. We don't know it is, but I mean it is, but it looks Gaussian. But the thing to note here is that the stochastic process we picked looked very rough. In fact, it was nowhere differentiable, but it was continuous at least. But actually, in reality, we might know more information about our function, right? So our integrand. So f star we might know is actually quite smooth, and therefore we might want to use a different stochastic process. So this is a stochastic process that is smoother, and we perform the exact same process where we repeatedly sample from the integrand from the random function, and for each of these samples we can integrate them and form a histogram. And we have the exact same thing. We have the empirical measure on the right, that again looks Gaussian, and if we collect the samples on the left, we get that plot there. And that's really what Bayesian cubature is you specify a prior stochastic process that embeds assumptions about our integrand, like smoothness, say, or you can embed other ones as well, like periodicity or whatever. And we can integrate the samples, integrate the stochastic process, and you get a distribution of the integral. And also we gather information from the integrand, condition on this information, and we get a posterior process, and we can integrate this posterior process and get a distribution of the integral. And so that's what Bayesian cubature is. So typically in Bayesian cubature, you model the integrand using a Gaussian process, and this is for good reason. So a defining characteristic of Gaussian measures is that they're closed under linear operations. Not all linear operations, but the most important and pertinent one being integration. And since integration is linear, the push forward of f through its integral is also Gaussian, with mean and covariance given by these formulas. In Bayesian cubature, you condition on information, and so you can actually easily derive the posterior expectation of the integral and the posterior variance of the integral through the previous slides formulas, using the posterior kernel and the posterior mean. And the important thing to note here that will come up later is that the posterior variance doesn't actually depend on the value of the integrand at the point set x1 up to xn. The value of the integrand only show up in the posterior expectation of the integral. And so this is quite important, and it will come up later on in the talk, so that's a thing to note now. Okay, so questions. We have discussed the cubature problem abstractly, Bayesian cubature, but certain questions that we might want to answer are the following. So how should we pick m and k? So this is really just prior specification. Second of all, how should we actually interpret the posterior variance of the integral? And so we have this final question, which is how you should actually pick the point set where we evaluate the integrand. And this is what the remaining of the talk will be dedicated to. So let's now move on to adaptivity. So again, we have the cubature problem, where you have the quantity of interest, the integrand, and the numerical method, the cubature rule. But really you have another bit of information. So the other thing you have is called the information operator, so the motivation for this is because the cubature rule actually only uses the integrand evaluations x1 up to xn, and so the information operator is the operator that takes in your function of interest, the f star, and returns the information you use in the numerical method. So for this case, because it's cubature, we only use integrand evaluations. All adaptivity is a property of the information operator. So the information in an adaptive method is gathered in a stepwise manner. So at each step, you use the current information, the current evaluations of the integrand, to decide on if you actually need to gather further information, so either you terminate or not terminate, and further, if we don't terminate, what information do we need to gather? So where should we next evaluate our integrand? Okay, so adaptive algorithms in classical cubature usually, but not always, have the following characteristics. So the termination is determined by a global error tolerance tau, which is just a real valued positive constant. Number 2, the information we gather is driven by local error estimates. So this is what we talked about at the beginning. So the absolute difference between two cubature rules. So as an example, this is notation for the trapezoidal rule. So this is the trapezoidal rule on the function f star in the interval a to b using n panels. So this is the trapezoidal rule on the original integrand f star from 0 to 1 with 10 panels here. So this is the notation that's important because we'll use it on the next slide. Right, so this is a prototypical example of a classical adaptive cubature method. So what you have, you have two cubature rules, Q1, that is the trapezoidal rule on m panels from the interval a to b, and Q2, that is the trapezoidal rule on 2m panels from a to b. And you perform the local error estimate, as we discussed before, the absolute difference between Q2 and Q1. So if this local error estimate is smaller than our global error tolerance tau, then we successfully terminate, we stop the algorithm, and we return Q2. If it's not the case, we halve our global error tolerance and recursively call adaptrap on the interval a to a plus b over 2, and from a plus b over 2 to b. So we're on the first half and the second half of the intervals with this new value of tau. So for a couple things to note, the sum of all these local error estimates on all these recursive steps, if you sum them all up, it will be less than the global error tolerance that you inputted at the beginning of the algorithm. And this is really the etymology of why this tau is called the global error tolerance. Furthermore, you can show that if our cubature rule Q2 is better than Q1, then the local error estimate is actually smaller than the true error, which is very useful. And furthermore, it is hopefully intuitively clear, and in fact we'll have examples later on, that these methods focus computational resources on regions over which f star is most difficult to approximate. So we now have the classical adaptive trapezoidal rule in action with this integrand, the blue function. So we now have the first step of the algorithm, where we have our Q1, which is this red line, the integral of the red line, and Q2, which is the integral of this green line. And so Q1 is the adaptive trapezoidal rule on m equals 1 panels. So this is the adaptive trapezoidal rule with m equals 1. And the green line is using double the amount of panels, so 2 panels. And so this blue bar here represents the global error tolerance tau at the first step of the algorithm. And if this difference is within this error bar, then we terminate, and if not, we carry on. So in this case, we carry on and we recursively call the adaptive trapezoidal rule on the next two intervals. So because it was outside the values, we do it again on the left hand side. It's still outside, so we call again. And so we basically have a binary tree representation of how the algorithm terminates. And again, we keep calling it because for each one of these it's outside the interval. Here it was close, but here it's far away. And then finally we terminate in a bunch of locations, in fact every location apart from these two, this one and this one. And we then finally terminate because these values are now within the local, are within the global error tolerance at that recursive step. So we finally get this output here, where the classical adaptive cubature method has focused more resources in these more difficult to approximate regions here. So that's kind of like the intuition. So we are now interested in adaptive Bayesian cubature methods. And so maybe the first natural way of creating one would be to try and cast a classical adaptive strategy into the Bayesian framework. For instance, we could take the previously specified adaptive trapezoidal method and recast it in the Bayesian framework. But so how do you do this? Well, the first thing to note is that the error and local error estimates are Gaussian random variables, but we also need a corresponding Gaussian process. So in the adaptive trapezoidal rule, the interpolatory scheme was the linear interpolant of the integrand evaluations. So we now need a Gaussian process whose posterior mean is the linear interpolant of the integrand evaluations. And so there is a famous one that has this property. In fact, it is the only Gaussian process that has this property, and it's called the Brownian motion. Right, so you can perform what amounts to an average case analysis of the adaptive trapezium method, where you are interested in computing the distribution of the error. And you can do this in this case. It's actually quite a hard computation. In fact, it's like an infinite sum of all possible terminations. What you can show is that the probability of the absolute value of the error being greater than the global error tolerance is greater than this value here. And so this is a negative result because really when an applied scientist would use the adaptive trapezoidal method, they would be assuming that this value is essentially 0. In actuality, in Bayesian cubature methods, you do not choose design points using a classical adaptive cubature method. Instead, you use things related to the posterior integral variance, this thing. And since as discussed, this only depends on the design points x, you can, in principle, determine the optimal choice of design points, so minimizing this thing for a given number of n. But unfortunately, this is NP hard, and so typically other methods are used. So what you instead typically do in Bayesian cubature is employ a greedy sequential adaptive scheme, where you pick the next point that minimizes the expected value of the variance. And so this is an instance of Bayesian optimal experimental design. So although we've discussed how design points are chosen, what you actually also need is a choice of Gaussian process. So typically one would pick what's called a globally adaptive BC method, where you have a family of stationary Gaussian processes, m theta and k theta, where k theta is a function of the difference between x minus y, coupled with the aforementioned acquisition function. So for example, you could have the Gaussian kernel, where θ1 is your amplitude and θ2 your length scale. Okay, so what's the issues of this from an adaptive point of view? Well, the stationarity assumption implies that the resulting design points will focus equally in regions where both the integrand is well and not well approximated. And that's really because stationarity kind of assumes uniform statistical properties over the domain. And furthermore, inference for theta, so these parameters that determine the kernel and the mean, is driven by the most difficult parts of the integrand. So for example, so this is the integrand is this blue squiggly line. The top plot shows the adaptive trapezoidal rule run on it. So we don't have a distribution, we just have a point estimate. And the plot shows the globally adaptive Bayesian cubature method sequentially chosen points, and you can see that in these locations where the function is flat, horizontal, you have quite large error bars where really you shouldn't. And it's because in this region in the middle, the spatially localized region in the middle, the inference for the amplitude parameter and the length scale are driven by this region here. And furthermore, you have uniform design points where really you should have more, in reality, you really want more design points in the middle because this is where the function is most complicated. And this is what the adaptive trapezoidal method here is doing. So this is the number of design points here. So this uses 91, this uses 41. Okay, another way of doing it of adaptive Bayesian cubature is using a transformed Gaussian process where you transform a GP, G, through a transformation T, which is assumed to be a stationary process. And so you can include global properties like positivity. So you can use a positivity ensuring transformation like squaring or exponentiating or whatever. When you use these positivity ensuring transformations, this results in regions over which the integrand is large being allocated more computational budget. Well, that might make intuitive sense and might be quite desirable. However, it's not always desirable because you could have regions where f star is simultaneously large but also easily approximated. For instance, regions where it's just flat and you don't need many design points or design points located there. So really the issue is the assumption of stationarity, the assumption of uniform statistical properties over the domain. And so what we really want is non-stationary Gaussian processes to focus more design points in the regions which are most difficult to approximate. So one way to implement non-stationary Gaussian processes is a Bayesian partition model, which captures non-stationarity by modeling the integrand as a piecewise stationary process. So it's globally non-stationary but locally stationary. So one of the ways of doing this is a Bayesian treed Gaussian process, where you represent the partitioning as a full k-ary tree. So another approach is the process convolution approach, where you take your Gaussian process and you convolve it. And when you do this, you get the following kernel, and you get a length scale function instead of a length scale constant, which determines local smoothness properties. So using this length scale function, you can encode prior knowledge about regions of the integrand. For instance, if you knew there was a step discontinuity at some unknown location, you could model the length scale as a constant plus a Gaussian centered at the what would hopefully naturally center at the step discontinuity. So the characteristic length scale controls smoothness. So on the left you have small values of L, and on the right you have larger values of L. So if you have a length scale function on the left, this blue function, so this is 1 over the length scale function, it results in sample paths that look like this on the right. So regions where the length scale is relatively larger, you get flatter, more smooth regions, and when the length scale is much smaller, you get more complicated regions here. And so that's the intuition. So you can just replace the stationary Gaussian process model with a non-stationary convolutional Gaussian process model, and you get a new adaptive Bayesian cubature method where you use the sequential procedure as previously discussed, called eAdaptBC. So now moving on to experiments. So this is an example comparing the eAdaptBC method versus the sequential BC method that uses the stationary Gaussian process. So on the left we have the eAdaptBC method working, on the right is the sequential. And if we proceed, we can see that the eAdaptBC method discovers the region that is difficult to approximate, whilst the sequential BC method does not. Right, so this is a more detailed plot of all the methods in action. So the top row is the adaptive trapezoidal method. As you can see, discovers the region through the local error estimates and places more evaluations here. And also the point estimate, you only get a point estimate for the value of the integral because it's a deterministic method. The next row is the standard Bayesian cubature method, where as you can see, the design points chosen are uniformly distributed, or uniformly on a uniform mesh over the interval. And furthermore, the error bars on these flat regions shouldn't really be there, and the reason they're there is because they're driven. The amplitude inference is driven by this complicated region in the middle. And finally, the eAdaptBC method, which has this length scale function, discovers this region in the middle and then naturally places more integrand evaluations there as well. So this is an error analysis of the eAdaptBC method versus the sequential stationary BC method. So this is run on a bunch of test functions, 200 test functions. And so the blue line here is the value of the error of the sequential BC method, and the red line is the error of the eAdaptBC method. On the bottom we have the n, which is the number of integrand evaluations, and the integrand evaluations in this problem. So on the problem on the left, this is in 1 dimension, and the problem in the right is in 3 dimensions. So the test functions were chosen such that they had a spatially localized region that was hard to approximate. So the reason why the eAdaptBC method performed better in both scenarios is because it was able to discover the length scale in this region was smaller, and therefore was naturally chose design points in those regions moreover better than the sequential BC approach. So we also ran the example on a robot, which is cool. So that's also in the paper if you'd be interested in looking at that. So essentially, you had a random distribution on how the robot's leg moved. So this leg here I'm pointing at with the laser pointer had some random inputs, and it was basically the distribution of the location of the robot after a certain period of time walking. Yeah, so that's the end of my talk. Thanks for listening. If you have any questions or queries, you could look at the paper, but furthermore, you could also just contact me if you have any questions. Thank you very much.